today we're going to look at infinite limits, which is looking at what happens when x gets really, really big. And so sometimes if we look at graphs that we've learned in the past, let's say we have a parabola, and as x gets really, really big, and in mathematics we put an x goes to infinity, what happens to the y values? Wow, that's a bad infinity sign. The y values go up forever as well. So sometimes we're going to say, as x gets really, really big, as x goes to infinity, y goes to infinity. And we can also have limits, like if I took an x graph, and I asked what happens as x goes to negative infinity. In other words, we're going in this direction. Can you see the y values would also go to negative infinity? But we've also seen graphs in math where it doesn't go up or down forever. Say, for example, do you remember this graph? A 1 over x graph. On this graph, we would say as x goes to infinity, y gets closer to 0 because it's approaching that asymptote. So when things go to infinity, we have different situations happen. Sometimes in our graphs, we had horizontal asymptotes, and then that limit would approach that value. Sometimes we have values approach infinity or negative infinity. This one is interesting because if I look at this one just one more time, and I say, if I look at the limit as x goes to 0 from the positive side, remember those left side and right side limits, from the positive side, that would be coming from this side, it would be infinity. And if I looked at the limit as x goes to 0 from the negative side, then it would be negative infinity. If I looked at the limit as x goes to 0, then this one we would say does not exist. Because one side goes to infinity, one side goes to negative. Now there are some textbooks, and I think your textbook might be one, where anything that's infinity, some textbooks just say does not exist. So you'll see more and more that if you can say something goes up forever, you'll write infinity. If it goes down forever, you'll write negative infinity. And only when it doesn't do the same thing, there's nothing you can say about it. As in this case, right? As you get close to 0, one side goes up to infinity, one side goes down to negative infinity, then we would say it doesn't exist. So when you're evaluating limits, like example 1, you're saying, here's a parabola. What's happening when x goes to infinity? Well, if you put really, really big values in for x, the y values get really big. If you think about the graph, like we just did, you see that it keeps going up forever and ever. So limits to infinity are a bit intuitive that way. Like if you can see the graph of x squared, you should be able to say that the answer to this is infinity. There's no algebra that we're really doing. We're not doing any kind of arithmetic. We're more thinking of a big idea of what's happening to the graph. And I mean, some of the algebra that you could do is you could be like, oh, I could throw in a big number, like 100. That's not that big. But this will become 100 squared, which is quite big. And then say if I throw in a bigger number, like 1,000, what happens? Oh, it gets even bigger. And then throwing in a couple of examples, you see the pattern. Oh, it's just getting bigger and bigger and bigger. But here, I think understanding our graph is really helpful for seeing what's happening. So here, what's the limit as x goes to infinity? Okay? If I thought about this graphically, I would say, oh, this is a line with a negative slope. it looks something like that. I don't know if I've drawn it perfectly, if it's steep enough. I'm not worried about that. I just want the general idea. And as my x values get very, very big, I hope that you can see that your y values are becoming very, very big negative numbers. So that's solving this limit from a graphical approach. From a numerical approach, what happens when I plug in 100? I get negative 305. If I plug in 1,000, I get a bigger negative number. If I plugged in 1,000,000, I would get an even larger negative number. And so from a numerical approach, I see that as I plug in bigger and bigger values of x, my answer becomes a larger and larger negative number, so it's approaching negative infinity. So then, numerically, or thinking about it, because sometimes you'll get graphs that you're like, I'm not quite sure I remember what the graph looks like. So then you might go to the numerical value, and you might say, if I plug in a big number, this gets big. If I plug in a big negative number, it's going to get big, but is it positive or is it negative? So here, plugging in a very big negative number into something cubed, a negative times a negative times a negative, this will become a very big negative number. So if you have any power that's bigger than 1, so any x squared, x cubed, x4, x5, even x to the 1.1, as x gets bigger, then that would go to infinity. Here's another one that we looked at before, the 1 over x graph. Here it's written as 1 over n. As n gets very, very big, your answer gets very, very small. Like I said, we can think, or we can draw a little sketch of the 1 over x graph. And we can see, as the x values get bigger and bigger, that the graph is approaching that asymptote, meaning it's getting closer and closer to 0. Right? In fact, it's getting as close as you want to 0, so that's why we would say that the limit is 0. Here too, what we're imagining here, you probably don't know what a 1 over n cubed graph looks like, let alone what 5 minus 1 over n cubed. So now we might take a numerical approach on this one. What would happen if I plug in a very, very big negative number? Can you see that this would get closer and closer to 0? In fact, if you have a variable on the bottom, whether it's an n or an n squared, n cubed, n4, n5, and you're plugging in a very, very large number, does it make sense that it's going to be going to 0? So if this part here, limit is 0, then the limit of this whole thing would be 5 minus 0. And just equal to 5. So if we have an r value bigger than 0 on the bottom, and you keep plugging in larger and larger things, the bottom will keep getting bigger and bigger and bigger, and as a result, that limit would equal 0. So now we're really sort of thinking in abstract ways. When do I have big numbers? Where are those big numbers? If I have a big number on the bottom of my fraction, I'm going to have something go to 0. If I have a big number on the top of my fraction, I'm probably going to infinity. And then I have to decide, am I going positive infinity or negative infinity? Two ways you can do this one. Okay? We can do it by the factoring part here, but I'm going to start with a graphical approach because you graphed 2n plus 3 over n last year in grade 12. Okay? The n's don't cancel out, so you would have known that there was an asymptote here. And you would have also known in this one something from grade 12, rational graphs. If you have a line over a line, or the same degree on the top as the bottom, like a parabola over a parabola, line over a line, you had a horizontal asymptote. And that horizontal asymptote was at the coefficients of that leading degree. So we've seen this already in grade 12. In grade 12, after you had this, you would have found your x-intercept to be negative 3 over 2. And once you had that x-intercept, you would have known this section had to go like this to go towards the asymptote. You could have plugged in a value, like if I plug in 1, I'm going to get 1, 5. And then that section would have to go towards the asymptote. So here we have our graph. And if I have my graph, what's happening as n goes to infinity? It's equal to 2. Now, mathematically, what a method for showing or proving that this is equal to 2 is we factor out the highest power. In this case, it is an n. So out of the top, I factor out an n, which would leave me with 2 plus 3 over n. And on the bottom, well, I guess I'm not really factoring out an n, because there's just an n on the bottom. But I factor an n out of everything. That would allow me to have these simplified. And some people find this much easier to do the limit of because they say this was one of our rules that if you're dividing by a very, very big number, it's equal to 0. So it becomes more obvious that the answer is equal to 2. Sorry, I have a notation problem here. There's no equal sign. There it is. I put an equal sign. It should be on that. So seeing that 3 over n, 5 over n, anything over n, that limit's equal to 0, this allows you to do that. That being said, I find many students, whenever you see the same power, the biggest one the same on the top and the bottom, it's just going to be the coefficients in front. And I will give full marks if you don't show this factoring out work and you just write equals 2, perfect. Because basically the idea is here. If I put a large number in for n, let's say 1 million, what's the top equal to, approximately? If I put in 1 million for n, my numerator is pretty close to 2 million. 2 million and 3, right? But that's pretty close to 2 million. In fact, if you had $2 million and someone gave you $3, you'd be like, wow, right? Some of you have probably played Monopoly. You've experienced this when you play Monopoly. First time around the board, if they land on, and you own Baltic, you're like, $4, pay up, right? Then, fast forward, you've played for an hour, you've got hotels all over the place and houses, but you still own Baltic, and someone comes around the board, and they land on it, And you're like, $4, don't worry about it, let's just keep going. That happens, right? Because you're at a different stage. That $4 makes a huge difference if you don't have bus money and need to go home, right? But $4 doesn't make a huge difference if you just sold your house and they're like, actually, we're only going to pay you $500,000 minus $4 because we don't have it. Are you okay with that? And you're like, fine, that's fine. Just happy to sell our house because it doesn't make a difference in that time. So when we put in really, really big numbers and we say, what is this actually, if I plug in 1 million, the top is close to 2 million, the bottom is close to 1 million, right? What's your answer going to be close to? 2, right? I'm not going to say, if I plug in actually 1 million, I'm like, what exactly is 2,000,003 divided by 1 million? To 7 decimal places. You're like, oh, I'd have to use my calculator to figure that out. But as a rough estimate, you're pretty good to say it's equal to 2 or close to 2. And that's what we're getting at with a limit. If I plug in an even bigger number, right? 2 trillion plus 3, that 3 is even more non-important than before. So with these ones, if the power is the same on the top and the bottom, the biggest power, it will always equal the coefficients in front. So you could now do very complicated, let's just do a nice complicated limit that looks like it would be, here, impress your friends and family. That looks super complicated. Just making up numbers as we go. But the biggest power on the top is a 7. The biggest power on the bottom is a 7. And so the limit of this will just be 8/3. And I'm fine without having to, like, the technique would mean, oh, let's factor an x to the 7 out of the top and an x to the 7 out of the bottom and cancel out a bunch of things, and then you have a bunch of parts that would go to 0, and you'd get 8/3. But I'm fine if you notice this, that you realize that it's just going to be 8/3. And the same thing is happening here as with the simple plus 3, right? When in the previous example when you had, was it plus 3? Plus 3 on the top there? That when you have 1 million, that plus 3 doesn't actually matter. The crazy thing here, when you put in 1 million and have it to the power of 7, technically in your brain, putting 1 million to the power of 6 is a very big number. But it actually doesn't matter. Because the 1 million to the 7 is so much bigger than the 1 million to the 6 that we can ignore everything with a less degree. Everything with an exponent that's smaller. Sometimes you have to be careful because they're not written in the same order. What's the highest power here is the 3. There we have both of our 3's. So you can basically ignore everything else and just look at those 2 terms. And the coefficient of the n cubed on the top is -3. The coefficient of the n cubed on the bottom is 8. And you can just answer it like that. If you wanted to show your work, this is what it would look like. You would factor out an n cubed on the top. You would factor out an n cubed on the bottom. These n cubes would cancel, and your limit go to 0, and this part would go to 0. And you're left with your negative 3/8 that way. As well. But the shortcut's really nice. It's just like, oh, so you just want me to write the answer? Perfect. It's important, though, to think about that and make sure while you're doing that every single time, does this make sense to me why I'm allowed to do this? And I don't think the concept is too crazy, and then I'm perfectly fine with just writing the answer. This one's interesting, because if you do -1 to the n, and you're putting in very, very big numbers of n, something happens. Because you realize that when you plug in an even number for n, it will equal 1. And if n is odd, well, an odd one would be -1. So this one keeps flipping back between 1 and -1, 1 and -1, 1 and -1. And even if n is huge, it'll still flip back between positive, negative, positive, negative, positive, negative. And what we're trying to do with the limit is we're trying to find, does it approach a single number? And here it keeps flipping between +1 and -1. And so when something keeps flipping and doesn't approach just a single number, then we say that a limit does not exist. So for this one, I want you to analyze it first. I want you to try to think about it graphically and numerically and see if there's a number that you think it approaches or if it doesn't exist on your own. Then we'll look at it graphically and numerically together. Okay. How did you do? The answer is 0. If we look at this graphically, this is an exponential function. Exponentials always have an asymptote at y equals 0. Exponential graphs always go through 0, 1, and they go through 1, whatever you have. In this case, the base is a half. You would have 1, half. Most exponentials, when someone talks about an exponential graph, you think of increasing, but because of this half, this one is decreasing. So there's a graph from last year from grade 12. Using that graph, what happens when x gets really, really big? Or when n gets really, really big, we can see that it's getting close to that asymptote and equal to 0. Numerically, you could plug in bigger values of n. I think sometimes in this case, it's nice. Keep putting that equal sign. Sorry. To use your exponent laws, that n would go to the 1 and go to the 2. This is technically the same as the limit as n goes to infinity of, because 1 to the n will just be 1. 1 over 2 to the n. And now we ask numerically, what's happening when we put in bigger and bigger values of n? The bottom is going to get huge. The top is going to stay 1. And if my bottom number is huge, I'm dividing by a very large number, then numerically it might be easy to see that this is equal to 0. And this limit, you are actually shown in grade 11. Do you remember, or maybe it was probably written this way, or sometimes it's written this way. The sum of the geometric series formula, if you are adding like 16 plus 8 plus 4, and I said, I'm only going to do that 18 times. How far will I have walked after 18 times? You would plug it into this formula. And n would be 18. And since I'm cutting my distance in half each time, we would have had this. But then in grade 11, you were introduced to an infinity formula for sequences and adding things up forever. And your teacher would have said at that time, oh, if I put in a very, very big number, this part goes to 0. And the formula became so beautiful. Just simplified completely to be term 1 over 1 minus r. That was your infinite geometric series formula. And you learned that formula back in grade 11. And you were introduced to an infinite limit at that time, but probably didn't realize. So we have as a general rule that anytime your r value was between 1 and negative 1, and this says absolute value is less than 1, does that make sense to you that that is the same as this? If absolute value is less than 1, that means that the r value actually is between negative 1 and 1. And anytime you have a fraction less than 1, and the limit as n goes to infinity with that exponent, that will always be 0. And you might also remember that your infinite formula for geometric sequences only worked when your r value was less than 1, when things were getting smaller each time. And we'll end with an example that I actually put up at the beginning of class. What happens when x gets close to 0? And this is a common misconception. If you ask many first-year university calculus students this, they will get this wrong, and they will say infinity. And that, I think it's human nature to be positive thinking. Just thinking that if I plug in something close to 0, dividing by close to 0 will get a very, very big number. And so I'll say positive there. But if we look at this one graphically, right, the 1 over x graph has an asymptote here, an asymptote here. And it does go to infinity if you come from the positive side. So we could say this, and we did this at the beginning of class as well, that if you come from the positive side, it goes up forever. But if you come from the negative side of 0, it goes down forever. So because my left side limit and my right side limit are different, we have to say that these do not exist.